Satellites are one of the most fascinating objects ever built by mankind, bringing us closer to becoming multiplanetary. But what are they? How do they even work? Let's start at the beginning. From Plato to Newton, the journey of human understanding evolved from philosophical reasoning about the universe to the establishment of fundamental laws of motion and gravity, laying the groundwork for the modern scientific exploration of the universe. This evolution of thought was accelerated by Copernicus and Galileo. Copernicus' revolutionary heliocentric model challenged the long-standing Earth-centered view of the universe, while Galileo's telescopic observations provided the empirical evidence to support this paradigm shift. Based on what Newton discovered during a time when the US and Russia were competing in the Cold War, scientists from both countries took Newton's laws and used them to start the space age. In Russia, a man named Konstantin Tsiolkovsky thought about how rockets could be used to travel in space. Meanwhile, in the United States, a scientist named Robert Goddard actually built and launched the world's first rocket powered by liquid fuel, showing that these ideas could really work. In 1957, the Soviet Union launched Sputnik, the world's first artificial or man-made satellite. It orbited the Earth and sent back the first messages from space, ushering in a new era of space exploration. The exterior was primarily made of aluminum so that it could be visible from Earth, and the interior contained radio transmitters, a battery, and temperature control systems. 4 external radio antennas were used to broadcast radio pulses. The satellite contained 2 radios on the inside which operated on frequencies that could be detected by ground stations on Earth. The main purpose of these transmissions was to provide information about the density of the upper layers of the atmosphere and the distribution of radio wave propagation in the ionosphere. Or in simpler terms, how do radio waves travel through the upper part of Earth's atmosphere? This information was really important for understanding how to improve communication technology. Fast forward to the most recent satellite launched, the Starlink satellites. These satellites, developed by SpaceX, are designed to focus on efficiency and mass production. Starlink satellites are strategically placed within the rocket's payload fairing, a protective nose cone designed to minimize air resistance or drag during takeoff, which is crucial for efficient fuel use. Like walking through heavy winds with an umbrella, you'd faster with a more narrow umbrella and with less effort than a wider one. Inside this payload fairing, the satellites are tightly packed in a flat, compact arrangement, allowing a larger number to be launched per mission. Upon reaching the designated orbit, the fairing opens, controlled by the rocket's onboard systems, which are typically automated and pre-programmed, and the satellites are sequentially deployed using mechanisms like spring-loaded robotic arms. After deployment, the SpaceX's Falcon 9's upper stage returns to Earth for recovery and reuse through controlled landings, often involving reigniting engines to slow down the descent and using landing legs to safely touch down on a landing pad or a ship. Meanwhile, the satellites autonomously initiate operations, unfolding solar panels and activating onboard systems. This entire process, from launch to satellite activation, is meticulously designed for maximal efficiency and safety. But how did these satellites even work? What are the materials involved and why? Well, Starlink satellites are a marvel of engineering. They are primarily built from lightweight and durable aluminum alloys, ideal for withstanding the extremes of space. This is because it is light and strong. It can endure the mechanical stresses during launch and can withstand extreme temperature variations in space, which can range from very hot when exposed to the sun to extremely cold in the Earth's shadow. But how do you actually build a satellite? Generally, when constructing a satellite, you would usually start with the assembly of a lightweight yet sturdy aluminum frame. Next, the solar panels on Starlink satellites are fitted onto this body of the satellite in a way that allows them to be compact during launch and then deploy once in orbit. They are typically mounted on extendable arms or hinges and unfold after deployment to maximize their exposure to sunlight. The solar panels on Starlink satellites function by converting sunlight into electrical power using silicon-based photovoltaic cells. If you're wondering how, when the photons from the sun hit these silicon cells, the energy from the photons energize the electrons in the silicon atoms. This energy is enough to break the bonds holding these electrons, freeing them to move. This movement of electrons creates an electric current, which is then directed into an electrical circuit. This flow of electrons can be harnessed to power the satellite's various systems, including communication equipment, onboard computers, and propulsion systems. The excess energy is stored in batteries to ensure continuous operation, maintaining the satellite's functions even when passing through the Earth's shadow. Another component in the satellite is the phased array antennas. They consist of numerous small flat rectangular plates or patches that generate radio waves using electrical circuits. These waves, once created, pass through phase shifters integrated within the antenna, then adjust the timing of these waves. The phase shifters, controlled by the satellite systems, delay or advance a specific point in the wave's peaks and troughs. This precise timing adjustment allows the antenna to align multiple waves to focus on a specific point on Earth, thereby strengthening the signal and ensuring a more stable and reliable connection. The reason it can do all this is through the onboard electronic system. It includes a powerful processor or CPU and memory to manage complex calculations and data storage. The satellite is also equipped with vital electronic components such as transceivers, which is a device that combines the functions of a transmitter and a receiver. It takes digital data from satellite's onboard computer and converts it into a radio frequency signal, which is then fed to the phased array antenna and directed it towards a specific ground station or satellite, and vice versa. It also includes sensors to monitor its health and control systems for precise navigation. Satellite control encompasses maintaining the satellite's orientation, ensuring it follows the correct orbital path, and managing the deployment of its solar panels and antennas. This comprehensive system ensures the satellite operates efficiently and maintains constant communication with Earth while navigating safely. But how does it navigate? The Hall effect thrusters, using inert gases like krypton or argon, are integral to Starlink satellites for precise orbit maneuvering and maintaining their position in space. These thrusters work by ionizing the gas and using magnetic and electric fields to generate thrust. If you are wondering how, electrons from a separate cathode are emitted into the thruster and collide with the gas atoms, knocking off an electron, making it a positively charged ion. And the anode, which is also positively charged and inside the thruster, repels these ions, creating thrust by the principle of action and reaction. And finally, some of the electrons from the cathode are also released into the stream of ions to neutralize them to prevent the spacecraft from charging up. In other words, think of it like a can of spray paint. When you press the nozzle, paint comes out and pushes back on the can just a little, but instead of paint, we are using gas particles. This process is efficient and well suited for the vacuum of space where satellites like those in the Starlink constellation operate. Alongside these, the satellites are equipped with GPS receivers, which provide accurate data on their orbital position. This GPS data is essential for ensuring the satellite remains in the correct orbit and for coordinating movements with other satellites, crucial for the stable operation of the satellite constellation. And to make sure the satellite doesn't freeze, Starlink satellites also have special thermal systems like a space thermostat to keep everything not too hot and not too cold but just right. These systems work like a combination of a sunshade and a heater. When the satellite gets too much sun, the thermal system reflects some of that heat away, and when it's in the shadow of Earth, the system keeps the satellite warm. This ensures that all the satellite's parts can work properly, whether it's in the blazing sunlight or the freezing darkness of space. Star trackers are also installed on the satellite and used to determine its orientation relative to stars. Inside each star tracker is a database that contains a map of the star patterns in the sky, known as a star catalog, featuring the positions of thousands of stars. The star tracker takes pictures of the space surrounding the satellite using a camera that is sensitive enough to capture the light from distant stars. After a picture is taken, the star tracker's computer analyzes the image to identify the patterns of stars it sees. It does this by comparing the positions of stars in the image with the star patterns in its catalog. Once the star tracker recognizes which stars are in the image, it can calculate the satellite's orientation. This is done by measuring the angles between the stars and using geometry to figure out the direction in which the satellite is pointing. The star tracker continuously takes pictures and updates its calculations so that the satellite always knows its orientation. This is important because satellites often need to adjust their position to communicate with Earth, perform observations, or conduct experiments. The orientation data from the star tracker is fed to the satellite's onboard computer, which then uses this information to control the satellite's thrusters and reaction wheels to maintain or change its orientation as needed. They are not affected by the Earth's atmosphere or magnetic field, which can interfere with other navigation methods. This makes them ideal for the precise altitude control required for missions, where maintaining a stable orientation is vital for keeping communication links strong and power generation consistent. These are obviously not all the components in a satellite, but they do represent the main aspects. Satellites are very important if we want to communicate across the world, travel to Mars, and eventually to other galaxies.